Hello, everybody. Thank you for joining us today. You are part of the 200 people worldwide who have registered to view this webcast, powered by Yole Development and System Plus, dedicated to the components for 3D sensing revolution. To quickly introduce us, Yole Group of Company provide marketing, technology and strategy consulting, media and corporate finance services, reverse engineering and reverse costing services, and as well as IP and patent analysis. With a strong focus on emerging application using silicon and or micro manufacturing, Yole Development, along with its partners System Plus, Nomade, and Pizeo, has expanded to include more than 80 collaborators worldwide, covering MEMS and imaging sensors, compound semiconductor, RF electronic, solid-state lighting, display, software, optoelectronics, microfluidic and medical, advanced packaging, manufacturing, power electronics, and battery and energy management. So my name is Faisal Kamasi, and I'm a global sales support and coordinator for Yole Development. Before we get started with the webcast, I would like to give you some information regarding the logistic. You have the possibility during the webcast to submit questions. In order to do so, you simply have to use the box at the bottom of the screen labeled Ask a Question. We will answer as many questions today as time permits, and for the remaining question, we will make a following up via emails within a week. Concerning the materials and content, please note that the presentation is available and downloadable in the resource section. You will also receive an email after the webcast within 24 hours with a link to the recorded session. So today, Yole Development and System Plus will share their analysis for you on components for 3D sensing, with in first a presentation of the market and in a second the overview of the technology and cost. At least a focus will be made especially on VCSEL. First, let's start with a presentation of components for 3D sensing by Pierre Cambou, Imaging, Technology and Market Principal Analyst at Yole Development. Pierre, please. We can't hear you, Pierre.
Yes, thank you, Faisal. So I will start my presentation concerning components for 3D sensing in the context of the release of iPhone 10 almost a year ago, and recent announcements from Xiaomi, Oppo, and Vivo. So the mobile market has evolved quite dramatically in the recent years. So from the photography and video use cases, the hardware has evolved in order to provide more performance and more features. So by first implementing additional cameras, which we've defined as embedded 3D computational approaches, now by the 2020, most smartphones will have embedded dedicated hardware. So this is the transition that we envision for the next 2 years with dedicated 3D cameras. So the use case of this additional hardware, has been quite well presented for more than 2 years now. So we've defined 3D sensing on the front side of the smartphone as a way to do easy unlocking of the phone with a touchless interface, with biometric. So security is a key feature of that is provided by 3D in respect to simple 2D images. The last type of use case that we've quite been provided by 3D sensing are gaming type of application and morphing. So morphing is kind of the animojis and the avatars, and those avatars there therefore can be used in eventually some gaming environment. So the next step would be to use video calls. But today, this use case is not there. This has been presented by Facebook for a while now, but this would require the ability to do 3D sensing for a long period of time, which is not really possible right now. So this is probably what could, the use case that could be implemented in the future. So the hardware that we've seen so far in the iPhone 10 was structured light approach, using structured light approach. So basically, it's based on two cameras. One is the global shutter 1.4 megapixel from ST. The other one is a RGB camera from Sony, and two illuminator. So one is close to the time of flight proximity sensor called the flood illuminator, and the other one is a dot illuminator. The dot illuminator is quite a complex component, and Stefan will present more in detail what we've discovered. So in the end, we have a very complex bundle of optical hardware on the front, quite of an optical hub with very different and complex technologies. So the penetration of 3D sensing so far has been led by Apple, and the cost was much higher than we envisioned at start. So the penetration was a little bit lower than expected, even though the revenue generated was in line with our predictions. We had three forecasts. One was in the green line, then the yellow, and then the accelerated forecast in orange. So today, as far as today, we are more on the green line, and eventually things will accelerate since the market is responding positively to this new hardware, new use cases. And we expect that by 2020, we'll even reach the accelerated penetration curve, and in order to reach more than 50% by 2023. The next step in the penetration of 3D cameras would be the introduction of rear 3D, which is a hard call today. Except gaming, there is no significant, very appealing use cases that tells us that we would generate more than 10% of penetration. So we will have to see if some mobile companies are able to present appealing use cases. So we are kind of waiting for the implementation of early adopters. So now, in terms of numbers, so this 3D hardware has been generating quite a significant market for components. And we can see that if we look in comparison to 3D sensors that were kind of in the high-end markets up to now in industry and medical, within 1 year, it almost doubled, and now it's accounting in billions of dollars. So from 2 to 4 in 2018, and will reach in the order of 18 billion by 23. The cumulative aggregated growth rate is in the order of 44% for the next 5 years. So let's get back to the hardware. So I presented at the beginning the very complex bundle of the 3D camera from iPhone 10. Stefan will look deeper into the components. It is interesting to notice the high cost of the solution so far. So the global shutter camera on the left, it can be split into different type of players. So silicon providers, like semiconductor companies such as ST, Sony, optic providers such as Genius Optical, Largan, Kantatsu. VCSEL provider Lumentum is a big winner of this of the Apple iPhone 10. And we have a focus by Pierrick at the end of the webcast. Manufacturing companies, ODMs such as LG Innotek and Foxconn have also a big part of for the assembly of this complex bundle of components. And in total, the 3D camera is more like a bundle of a 2D and a 3D reaches $20, probably impacted by some yield. So the cost is more than triple of a single RGB camera that we've seen so far in the mobile world. So the companies involved in this ecosystem are numerous. There are the sensor companies, the 3D camera module manufacturer, the illumination companies essentially providing VCSEL have a central role in 3D since it is active imaging. Then the optical path, either for the receiving side or the emission side. Then the software and computing is also quite a key part of the ecosystem, and also 3D system design. So all of this ecosystem is serving a very small number of OEMs, so the main ones being Apple, Huawei, Oppo, Xiaomi, Samsung, and Vivo. Thank you for listening to my part. Faisal?
Thank you very much, Pierre, for this interesting overview. Once again, to the audience, please do not hesitate to ask questions using the Q&A button for the Q&A session at the end of the webcast. So let's continue with a technology analysis by Dr. Stefan Elisabeth, RF sensor and advanced packaging costing engineer from System Plus Consulting. So Stefan, the floor is yours.
Thank you, Faisal. Hi everyone, I'm Stefan Elisabeth, cost engineer at System Plus Consulting. And I'm in charge of RF, image sensor, and advanced packaging, and I will present some recent observation made by System Plus on 3D sensing solution to see where we are going in this revolution. To begin with, we present the ecosphere. 2018 is a new year for the whole company involved in 3D sensing. Since the release of the Apple iPhone X and its Face ID features, several companies have taken the tail. In this year, we will see mostly Chinese company integrated 3D sensing featuring face recognition. And today, many manufacturing companies share the inside sphere, providing several solutions to OEMs: dot projector, near SOI imager, global shutter, VCSELs, etc. And the integration and the cost related are two main characteristics separating the solutions. Here, I will try to give some clue on these two parameters. So, as we know, Apple, Lenovo, and Asus are OEMs that have already released 3D sensing modules for 3D recognition or for augmented reality. Here at System Plus, we have already analyzed and published some reports on these modules, revealing the major supplier in all supply chain. And for the next generation of smartphone featuring 3D sensing, we have already some clue for some of them. For example, we know that Xiaomi and Mantis Vision has announced their partnership on the 3D sensing modules at the front featuring dot projector. And we have also estimated that Vivo will feature the new generation of near imager from Infineon and PMD. Among all of these solutions, three main technologies are used: structured light, stereo vision, and time of flight. So in the Apple iPhone X, we have two technologies that can be found for the face recognition. First, time of flight is used with a fluid illuminator and a near imager to detect the presence of the face. And after, we have a structured light behavior using a dot projector and the same imager than before to recognize the face. After, we have also the stereo vision. We are aware that the Intel RealSense is more dedicated to industrial purpose, but a stereo vision could be possible for smartphone, I think, in the future. And so here in the Intel RealSense, we can see which kind of technology that can be used. And here there is two identical imager and a projector that is used to perform the stereo vision. The projector is using a VCSELs component and lenses modules in a fluid illuminator configuration. And finally, we have the time of flight, which is a very simple system. It's composed by a near imager and a fluid illuminator. The fluid illuminator could be made with a VCSEL and a diffuser, and the near imager could be just a photodiode-based VCSELs. Beside the basic components realized using the 3D sensing, some complementary sensors are integrated in the final device to complete the object sensing. For example, in the iPhone X, a proximity sensor is used to detect a user proximity. Also, RGB camera is added as in Intel RealSense and the Lenovo Fab 2 Pro to complete the sense object with texture. And in Fab 2 Pro, a global shutter camera is used for motion tracking in augmented reality application. So now we will see the three solutions. First, in the Apple solution, three companies has won the design. Lumentum, who supplied the most of the VCSELs. AMS, who provide the ambient light sensor and also the dot projector via Heptagon. And ST Microelectronics, who supply the proximity sensor and the near imager using SOI substrate sourced by Soitec. All of these sensors are aligned from the imager to the projector to have the better configuration to sense the face. And all the 3D sensing modules are all on the same metal case with a flex PCB for each module. And if we take a look at the cost of the 3D modules, we have the bigger part related to the dot projector with more than 60% of the cost. And taking out the die size, we can see that the VCSELs for the dot projector is the more expensive die in the modules at nearly 20% of the cost. And concerning the Intel and its real sense, we have an example of stereo vision application. But targeting industrial application, the form factor and the VCSEL dimension are bigger than expected for consumer application. But the component could be the same at lower scale. Here we have two main identical cameras supplied by OmniVision. That is two global shutter offering black and white and near sensing at 1 megapixel of resolution, and a projector featuring more than 6K cavities. All of these result in high heat generation that need thermal dissipation techniques like thick copper support or heat sink. And this configuration resulted in a cost module at nearly $30, which is too expensive for smartphone application. But if we take a look at the breakdown, the VCSEL has almost 30% of the cost, and this could be reduced in case of smartphone application. And finally, in case of time-of-flight application, Lenovo and Asus features a fluid illuminator from Princeton Optronics, now IMS, and a near imager from Infineon and PMD. And here, with a very large pixel size on the large die, Infineon and PMD managed to provide augmented reality experience in the smartphone. And this module was the first on the smartphone market. As the VCSEL was very small, the higher cost was mainly attributed to other components and to the imager. But for the next generation of the sensor, Infineon has claimed to reduce the size of the modules and also to integrate all the other components in the imager except the fluid illuminator. That could, of course, reduce the global cost of the modules. And so to conclude my talk, I will come back to the component cost of the three systems that we have presented. And one sentence came all along the presentation in these three cases, the VCSELs, that take a non-negligible part of the module cost. Indeed, the structuration of the light is the main key of all these technology. And for the next years, we could expect a growth in the market share of these consumer application on VCSEL components. But Pierrick, after next speaker, will provide you more information about that. Thank you for your attention.
Okay, thank you very much, Stéphane, for this interesting analysis. Now, as Stéphane introduced, it's time to Pierrick Boulay, solid-state lighting technology and market analyst at Yole Development, to provide an overview of VCSEL technology. Pierrick, please.
Thank you, Faisal, for the kind introduction. So my talk will be focused on the illumination part of 3D sensing components, which are VCSELs. I will mostly talk about the VCSEL industry and also manufacturing. So first, what is a VCSEL? So a laser diode family can be divided in two basic structures. So the first one is edge-emitting laser, which emit light from the edge of their structure, and surface-emitting laser, which emit light from the top or the bottom, in some cases, of their structure. VCSEL is the acronym for vertical cavity surface emitting laser and is considered as a surface emitting laser. It can be packaged in SMD, like LEDs, or in more classical package like TO46 package. And usually a VCSEL is hermetically sealed in a package with an optical element. VCSELs are similar to LEDs because they can be tested during the manufacturing process, which is a huge advantage compared to edge-emitting laser. For edge-emitting laser, we need to wait the end of the manufacturing process after dicing to be able to test this kind of laser. The other advantage of VCSELs is that it can be built in two-dimensional arrays. So here is the timeline of the main application for VCSELs. So here we can see that the first demonstration of VCSELs was done in 1979, and the first industrial application appeared in 1996, where VCSELs were used in datacom applications, and VCSELs are used for short distance application, typically in data centers, with a distance lower than 100 meters. So basically, the datacom application generates the highest volume of VCSELs during almost 20 years before the introduction of VCSELs into smartphone applications in 2014 with the laser autofocus and the proximity sensing application. And the entry in the 3D sensing area started in 2017, and it is still the beginning of the 3D sensing area, and we expect it to continue and generate very high volume in the next years. When we look at the VCSEL industry, so we have an ecosystem with AP wafer players, foundry players, and device manufacturer, which can be split in three categories: IDM, fabless, and manufacturer, which are using VCSELs only for their personal use. In the AP wafer category, IQE is the leading player by far, and is currently supplying AP wafer to almost all VCSEL manufacturers. And in this category, Finisar, Philips Photonics, II-VI, and Lumentum and Princeton Optronics appear as the leading player. They are all related to the 3D sensing application, and most of them are part of the Apple supply chain, like Philips or Lumentum or II-VI. The other players in the third category, like Fuji, Xerox, Ricoh, or Trillumina, are involved in printing, in laser printing for Fuji, Xerox, and Ricoh. And Trillumina is involved in LiDAR application for automotive. When we look at the evolution of the player, so all the players were involved in datacom at first, and then when the VCSELs were introduced into smartphone, some of them moved to this new market, and we also saw the entry of new players like Lextar, Epistar, ChangeLight, or Sanan. Still in the industry trends, when we look at the investment and merger and acquisition that occurred in the past, we can distinguish three eras. So the first era was the datacom era until 2008. with the acquisition of Honeywell by Finisar and the acquisition of Photonics by Philips. And then almost nothing happened during 10 years, and it was only starting in 2016 that we saw a new era, the 3D sensing era, where a lot of investment and merger and acquisition occurred, and we expect more investment and more merger and acquisition to appear in the next years. When we look at the manufacturing process of VCSELs, so it is showed here in the slide. There are 3 steps which are really critical, which are the epitaxy, the laser etching, and the wet oxidation step, where we need control. The epitaxy step appears as the most challenging one, as it will determine the entire manufacturing yield. As an example, in the epitaxy manufacturing, a shift of 1% of uniformity will lead to a deviation of plus or minus 10 nanometer in wavelength. So we observed a lot of investment into metrology to have a better control of these manufacturing steps. When we look at the VCSEL specification compared to the application requirements, so we see that there is a large variety of VCSELs, both in terms of surface of the VCSEL die and in output power. So basically, the datacom and proximity sensor application require low power and and VCSELs with a limited surface up to 0.06 square millimeter. And when we go to 3D sensing, the surface of VCSELs increases with the number of cavities up to 1.3 square millimeters and 1 watt in power consumption. And then when we go to LiDAR for automotive or industrial application, the surface of VCSELs increases dramatically up to 75 square millimeter and 40 watts. So in manufacturing, VCSELs can be manufactured on different sizes of wafers. Typically, datacom VCSELs are manufactured on 3-inch or 4-inch wafers. When we look at the market volume, and in 2018, the VCSEL volume was estimated at 132 million and is expected to reach 213 million in 2023. So manufacturing on 6-inch wafer is not necessary, mostly because VCSELs for datacom require a very precise wavelength, and manufacturing VCSELs on 6-inch wafer will generate less uniformity and tolerance and decrease the manufacturing yield. When we look at the consumer market, so the volume in 2018 was about 500 million and is expected to reach 2.9 billion in 2023. So here we have 2 cases. For proximity sensing, that use very small VCSEL dies. VCSEL are manufactured on 4-inch wafers. So in the future, it can still be manufactured on 4-inch wafers, depending on the volume increase. If volume increases a lot, transition to 6-inch will be necessary. But when we look at the float illuminator or the dot projector, which are much bigger than for the proximity sensors, here the manufacturing on 6-inch wafer appear necessary to meet the high volume demands and the price requirements. And for automotive application like the LiDAR, so currently there is no volume in 2018, but we expect it to reach 3 million in 2023, depending on the ability of VCSELs to replace edge-emitting laser in LiDAR application. So I would like to conclude my talk with the market forecast in volume and revenue. So in volume, the VCSEL market is expected to grow from 650 million units in 2017 to 3.3 billion units in 2023 at a CAGR of 31%. And the consumer part of VCSEL will represented 75% in 2017 and is expected to represent 90% in 2023. In revenue, the VCSEL market revenue is expected to grow from 331 million in 2017 and is expected to reach 3.5 billion in 2023 at a CAGR of 48%. So here the consumer segment will represent 50% in 2017 and 90% in 2023. So this is the end of my talk. Thank you for your attention.
Thank you very much, Pierrick, for your relevant presentation. So we received a lot of questions. We have about 20 minutes, so we are now going to wrap up with a Q&A session. We will answer as many questions today as time permits and follow up via email on the remaining questions. All right, so Pierre, I've got one question for you. Will fingerprint be replaced by 3D cameras?
So thank you, Faisal. So yeah, this is quite interesting question since on the iPhone 10 that was the big event, the disappearance of the fingerprint to be being replaced by 3D camera and the Face ID. Will it be duplicated all along the market? And that's the big fear. But what we've observed so far is that smartphones market are not evolving the way, very uniformly all across the market today. I mean, the smartphone is more and more segmented. There is a luxury niche where Apple placed the iPhone 10, and we don't expect the 3D to reach the full market anytime soon. So when we say 50% penetration within 5 years, that also means that 50% of the market in the order of 1 billion unit smartphone will not be using 3D cameras. So there will be space for many, for different approaches, and depending the price of the handset, different technology will be used.
Okay, thank you, Pierre. Stefan, a question for you. What will be the next move of Apple concerning 3D sensing?
Thank you, Cecil. Yeah, it's quite a good question also. We have seen last year that it was the 10th anniversary of Apple's, and they want to make a big move, and they released the 3D sensing at the front to the face recognition. But I think for the next generation, they could focalize them on the front on the back, of the smartphone, and integrated augmented reality in the next generation of smartphone. And to do so, I think they could use the same way as Lenovo has introduced the AR experience. They could use component like 3D illuminator coupled with near imager to look at the scene, and they could use also a global shutter from. Why not reuse the sensor from ST at the back? It could be interesting, and I think it could be done also.
Okay. Thank you, Stefan. Pierrick, a question for you. What will be the place of new entrants in the VCSEL industry?
Yes, Stefan. So, like I mentioned earlier, we expect new entrants to appear in the industry. So we will see two types of new entrants. So there will be players that will enter the VCSEL industry by merger and acquisition, like Osram did with VCSEL recently this year. So Osram has currently acquired VCSEL, and they will use VCSEL knowledge to manufacture VCSELs. And we also see new entrants like Epistar or Sanem, which are coming from the LED industry, and use their MOCVD reactor to manufacture VCSELs. And these new entrants will try to focus on the consumer market or automotive market, which are the most promising market generating high volume VCSELs. But the process of manufacturing VCSELs is very long in terms of development and to optimize the process. And manufacturing VCSELs do not rely on buying a new MOCVD reactor. It needs a very long time to optimize the process and qualify VCSELs with potential customers. And we expect that some new entrants will arrive too late and will not be able to reach a noticeable share of the market.
Okay, thank you, Pierrick. Pierre, question for you. Will world-facing 3D cameras use the same technologies as the front?
Yes. So I mean, this is a discussion that Stefan got a few minutes ago. So what's the next step? So I've mentioned it at the beginning of the presentation. We all expect some implementation of 3D on the world facing, so on the back of the phone. So our position at Yole has always been that any of the technologies are available. I mean, from stereo, structured light, and time of flight. Those three technologies. It will really depend on the application, the use case, the maturity of the technology and the accessibility in respect to the OEM that really want to implement this technology. So it's really a decision each of the OEM will make. Our opinion is that on the rear, it's a different story. So it could be a structured light using global shutter. It could be a time of flight, and there are several providers, Sony, PMD, and probably ST will also provide some time of flight at some point. Not mentioning Omnivision and other possible players. And for the stereo approach, the same global shutter could be used. So there is a lot of possibilities, and the problem of the supply chain and the complexity that it is involved in 3D sensing makes me favor a duplication. So probably if we are talking about Apple, probably the same approaches could be duplicated on the rear. But we've seen the Vivo, for example, is implementing time of flight on the front. So again, we could see some players using time of flight. The big complaint being price. So the speed of implementation will probably be very, very low.
Okay, thank you, Pierre, for your feedback. Stéphane, one other question for you. What is the big difference between the global shutters from Omnivision and ST Microelectronics?
Okay, thank you. For the global shutter of Omnivision, we know that it's a photodiode based pixels. It's a usual technology, but we have seen that ST has published in the Apple iPhone 10 a new way of global shutter sensor using SOI substrates, deep trench isolation also. Together, they managed to increase the quantum efficiency and reduce the noise of the sensor. And this way, they finally get to I think performance that could compete with global shuttering devices today.
Okay, thank you, Stéphane. Pierrick, one question. Why MOCVD is used for epitaxy?
So for the epitaxy step, so it can be realized in two ways with two different reactors. So the first step is using MBE reactors, which provide a good uniformity, about 0.5% across the wafer, leading to a wavelength deviation about 3 nanometers. But the process is, even if it is precise, even if we have a precise material deposition on the wafer, the process is slow and is mostly preferred for R&D or for specific device. For MOCVD, the uniformity is about 1%, leading to a wavelength deviation about 10 nanometers. But this process enables a fast growth and therefore is widely used for mass production. And when we look at the VCSEL manufacturers, they are all using MOCVD reactors in 6-inch for consumer application from Vico or Extron.
Okay, thank you, Pierrick. One question Pierre, what is the power consumption of structured light camera in the iPhone X? iPhone 10, let's say.
Yeah. So the power consumption is probably one of the most limiting, big limiting factor of the current approach. So when in the deep process, we've seen the packaging approach all ceramic based and with the inclusion of aluminum nitride inserts. So on the dot illuminator and on the flood illuminator, which is an indication of the heat dissipation needs for those two illuminators. So we haven't seen that in the past ever. So this is a big concern, probably. And the order of magnitude, so we don't have measurements, but the order of magnitude is several hundreds of milliwatts. So maybe up to the watt. This is in the presentation of Pierrick. And this is also the reason why this 3D sensing cannot last for long periods of time. So it's the videos or the 3D capture is only in the order of 1 second or few seconds to unlock or to do a short video.
Okay, thank you, Pierre. Maybe one last question as we are running out of time. So, Stefan, what is the difference about the VCSEL chip using time-of-flight proximity sensors and 3D time-of-flight sensing?
To answer this question, we could take the example of the Apple iPhone 10. We know that the proximity sensor uses a VCSEL chips, but it compared to the VCSELs used in the dot projector, the chip is very smaller, and also it has less cavity. Taking this difference in account, we can say that basically the proximity sensor doesn't take a lot of power consumption and power light emitting, so the chip is smaller compared to the VCSEL used in the 3D dot sensing that required higher light power and also consume more, as Pierre said before.
Okay, thank you. So the webcast is ending. So thank you, Pierre, thank you, Stefan, and thank you, Pierrick. Within the next 24 hours, you will receive an email that will include the recorded session. Please feel free to share the presentation with who will benefit from the information that has been presented, and find all our information and analysis and reports on our imicronews.com webcast. Just the last information, we are also organizing in collaboration with the CIOE, a forum in Shenzhen. It will be in China. It will be in September 6th on 3D sensing for consumer. So 3D sensing for consumer. Do not hesitate to attend it. Companies as ON Semiconductor, LeaderTech, Valeo, and more will be presenting. You will receive more information in the next emails about this forum. Thank you for joining us today. Do not hesitate to contact us if you have additional questions. We'll do our best to answer. You can find your appropriate contract on the last slide of the presentation. Have a good day. Bye-bye.